Yeah, so before we get started with the actual webinar, I'd like to just remind you of some upcoming webinars we have here in the coming weeks. In 2 weeks from now, Itai Aina from the University of Sydney, and then there's more coming. We will have a bit of a break in August, but then we'll resume in September. But onto today's webinar, and as I said, it's a webinar that I've really been looking forward to, this multi-scale modeling of granular media. So multi-scale modeling is something that has been, let's say, in the news for a long time, and it's something that a lot of people are talking about. It's something that has been recognized for a long time, that the macroscopic behavior of granular media is a consequence of the microscale and mesoscale processes. So if you could link these different length scales, then somehow you could have a more rigorous way of modeling these materials. So it's something that this idea has been out there for a long time, but it's something that, as far as I know, has in many ways not really materialized until this work of Professor Zhao's group. So I'm really looking forward to this, and I hope we'll have an interesting Q&A session afterwards. You are welcome to, if you have questions, you can do it during the webinar or after the webinar. Type in your questions into the Q&A box, and also if you raise your hand, we can unmute you and you can ask a question in person. So with that, I will hand over to Jidong.
Right. Can you hear me?
We can hear you, yes.
Let me share my screen. Oh, you can start. Can you quit your screen? Because I cannot share my screen now.
Okay. I'll stop sharing mine and then.
Yes.
That's it.
Can you see my screen?
Yeah.
Okay. First of all, I wish to thank Professor Christian Queppenhoft for inviting me for such a wonderful webinar series. I know that there are a lot of other webinar series before, and it's my great pleasure to introduce my research at Hong Kong USD, and also wish to thank Dr. Zhao for advertising this webinar in the Chinese WeChat groups, and that could get more audience here. So today I'm going to introduce our research on the multi-scale modeling of granular media. Okay. So let me. Our research focuses on granular material. So granular material are the second most processed material in industry. And so we know that the first one is water, okay? And so they are important, and indeed, they are so common in our daily life. And every day when you drink a coffee, the coffee bean, coffee powders, the sugars, salt, food grain, and the medicine tablet, and also the makeup powders for our ladies, and the chemical powders, the mine products, the fertilizer, the sand, and all these things are granular material. And even when we do this moon and Mars landing, and the first thing that we need to deal with would be the granular media, like the soil on the moon and Mars. And indeed, some people working on the planetary science, and they treat this all the stars and planets as a granular media as well, and they can develop research here. So today I'm going to focus on a quite typical granular media, sand here, and this is quite common to our civil engineering and geotechnical engineering here. Okay. And so I'm going to focus on two particular property or features of granular sand. Okay. For example, they have a multi-scale nature, and they have a multi-physics properties that we have to deal with here. And so the multi-scale nature, as you can see here, the typical sand particles, they are in the range of millimeter or 0.1 millimeter, that kind of range, that microns micron length scale. Okay, but when we deal with engineering problem like in our civil engineering, and we are dealing with hundreds of meters or kilometers, that scale here. Okay, and so the length scale will have a several magnitude of difference that we have to deal with. And when we consider the sound, but the individual particle and to an engineering scale here. So this is the one aspect that I'm going to today focus on. The other aspect would be multi-physics. We know that sound is typical porous media here. Okay, so the pores in between some particles, they can be fully saturated or partially saturated by water. Okay, and so the degree of saturation will affect the sound behavior. For example, when we pour dry sand on a level ground, and we can form a certain sound pair with certain rippled angle. Okay. But when we saturated, when we put certain water in the sand, and we can build a sand castle and put it hot. But when we add more water in sand, and then the sand castle will collapse here. So the content can be important. And so there's interaction between the water, even gas, and the sand particle will affect a lot of engineering processes like this offshore and coastal engineering, and also this land reclamation in seafront for a lot of cities around the world. Also in the embankment dam situations that where there's piping and other process and soil erosion, those are the important processes where the soil fluid interaction is important here. Okay. Of course, in the more other engineering like a debris flow, this is also a process that where the particle, soil, and fluid interaction play a very important role here. And so my research has been focused on the multiscale and multiphysics modeling of granular sound here. Okay. And so first, we consider that when we consider granular soil, granular sound, we have to really separate different scale in order to really tackle it. For example, for engineering scale, we could typically have a range of length scale, range of kilometers to 100 meters here. And for a particle scale, we could range from, for example, 1 millimeter to 0.1 millimeter, that length scale here. And in between, we have a so-called mesoscale, and the mesoscale is typically a laboratory sample size scale. For example, when we prepare a element tester samples, and that sample size could range to several 50 to 70 centimeters to up to 1 meter. That is big size samples here. So we typically have these three typical length scale to deal with here. Okay. And so the methodologies that have been adopted in the history and in the geotechnical engineering is typically that we deal with a engineering problem, a boundary value problem by using this continuum mechanics approaches here. For example, we can't really assume a constant model, and we calibrate the model parameters, and by conducting laboratory tests, and then validate the model by some physical testing, and then apply to a boundary value problem to predict the performance here. Okay. So numerically, that we can use finite element method, material point method, or SPH, and other continuum-based method to deal with it. Okay. So this is a prevailing method. For example, I think maybe 80% or even more than 90% in practice, they have been using this continuum-based method to solve a problem here. And they are quite efficient and effective in many ways, but there are some big issues. For example, they could be costly. You have to really use a lot of laboratory tests. And a lot of model performance will be loading path dependent and also the problem dependent. For example, and you have to really propose a model which is good for a monotonic loading, but not good for secular loading. Okay, and a lot of when you have to really deal with a complicated situations, you got to really involve a lot of phenomenological model parameters, and those model parameters is hard really to calibrate, and also many times they don't have a physical mapping. So those are the continuum-based method. And another popular method in recently is a so-called micromechanics, and they start from a individual particle levels and then put a lot of particles together and to consider their interactions here. For example, they consider the grain mineralogy, the morphology, surface attributes, and contact, friction, loading, sliding, and breakage, and those particle level physics here. They put them together, consider their interaction here, and to get the collected behavior from a packing we call RVE, or representative volume element, to get this mesoscale response here. Okay. They could really tell us some physical insights from this particle level microstructure here. Okay. But the major drawback for this micromechanics approach would be normally they are, for example, DEM, they are computationally very costly, and also it's very hard really to get a very accurate particle scale or characterization, for example, the morphology, the friction, and other things here. And people have developed a physical or digital mapping approach, but it's like a one-off mapping. You cannot really generalize to a class of material here. And so far, micromechanics approach and like DEM, for me, my take is they can best serve as a virtual element test. You can really using DEM to really get a replace partially this our traditional element test to derive the material response and to get some insights from this particle simulation here. Okay. And so that's the two major methods adopted in for granular sound study here. So today I'm going to introduce our research is based on the hierarchical multiscale modeling. The purpose is to demolish the walls between the three scales here, and to enable direct dialogue among these three scales. And this is also quite unique for granular media, because we know that multiscale, this term has been quite popular in engineering, in material science, but material science could be different from us. And they could have a lot of other features, like they have a periodical microstructure, but for granular media, we don't have a periodical microstructure. And the granular media response is loading history and path dependent. And it is a typical porous media, so the pores can be filled partially or fully by liquid. Okay, and also we need to have this hierarchical multiscale modeling framework is going to enable a multiple way information passing, meaning that we don't just do one way homogenization. We need really tell both upscaling and downscaling. So this is what we wish to really to develop here. So the idea is based on a continuum discrete hierarchical coupling here. Okay. That is we still use the strengths of this continuum-based computation method, like finite element method and material point method here, to simulate a boundary value problem at an engineering scale here. And we still adopt this discrete element method for this mesoscale and a microscale simulation from the particle scale. Okay. But we develop a hierarchical coupling scheme to try to bring them to marry the two, the continuum and the micromechanics approach together. Okay, and to combine their strengths will try to avoid, try to eliminate, try to reduce their weakness. Okay. So here's how it goes. Okay. For example, if we want to really develop a hierarchical coupling between finite element method and discrete element method here, okay, and we know that finite element method can have a great advantage really to manage a boundary divider problem for example, quasi-static loading and static loading for a 2D and a 3D here. And also we can really to develop a boundary divider problem to solve an engineering skill problem like this, a retaining wall, a footing problem, a other engineering problem here. So this is the strengths that our finite element method offers us here. Okay. Well, for the discrete element method, they can really to allow us to develop all kind of contact model and friction model to develop a 2D and a 3D simulation here. If you want really to incorporate the shape effect, you can develop a different particle shape incorporated into this DEM simulation here. If you really want to map this realistic particle shapes, you can develop this kind of city mapping to directly use in the DEM simulation here. Or if you can further incorporate the other mechanism like particle crushing in the DEM simulation here. So DEM simulation can help us capture this particle scale or microstructural mechanisms, all kind of mechanisms into the simulation here. So here's how it works here. The hierarchical coupling between FEM and DEM is working in this way. For a typical boundary divider problem like this slope problem, we still discretize this domain by a finite element mesh here. Okay. And you know that in continuum approach, we need to assume a constant model here. And by here, we don't assume any constant model. We embed at each Gaussian point in this finite element mesh by a discrete DEM packing here. This DEM packing will serve as a representative volume element. And this RVE will receive the deformation other condition or incremental displacement at the boundary conditions. And at this boundary condition, DEM will get a solution. And with this deformed packing of this DEM, will extract those quantities like stress, increment stress, and tangent operators to this FEM. And those quantities will be required really to the input for the DEM to get a solution. So this circle will go on here. And so at each Gaussian point, and we actually let the computation memorize this loading history of each RVE here. Okay, so in this one, this can help us to bypass this continuum phenomenon, logical assumption. We don't have to really assume a model. And also it can help directly to get this meso and macro scale details here. So it is a two-way information passing. It's a downscale from this FEM to this DEM here, and also it's upscaling as well. We have to really transfer back this required stress under tangent operator here. Okay, and so in this information passing, and this will enable a direct link between this the continuum level phenomenon and with their underlying microstructural physics here. And so it also allows us to handle this loading path and state-dependent behavior in a granular side here. Okay, and so this is the way that I want to emphasize. It's a two-way information or message passing scheme by this coupling here. I'm going to demonstrate. I'm not going to really introduce in detail, but this technical detail. But I'm going to demonstrate the major features here. For example, we can simulate a lot of interesting phenomena, like string localization, like other things, and to see that how we can establish a continuum and particle scale bridging, this linking by this hierarchical modeling here. Now, for example, we have we have a boundary value problem. This is back to shear problem, and we simulate by finite element match here. And at each Gaussian point, we can insert a representative volume element by DEM here. And this RVE is summed up, is prepared by this elongated DEM particles and to represent the different anisotropic body plan here. Okay. And then here, this is a animation here. Under smooth boundary condition, under rough boundary condition, we observe that the formation of shear band is quite different. For example, smooth give us a single shear band, and the rough boundary will give us a cross-shape shear band here. Okay, and so this observation commonly you can really observe in the continuum approach by finite element method here. Okay. And we can further inspect, for example, those shear force applied, reaction shear force generated at the loading pattern. This will be a triggering mechanism that why in a rough boundary case where the cross-shape shear band is developed. Okay. And also we can extract other information rather than shear strength, which is normally used to indicate a shear banding here. We can, for example, extract this particle orientation-based fabric tensor and extract this fabric invariance and to use that as an indicator of this shear band here. And we can further extract this cumulative average particle rotations. This can be calculated at the representative volume element we inserted at each Gauss point of this finite element match. They correlate very well with this shear strength. They can be used as a shear localization indicators. But I wish to demonstrate with the same example by how we can establish this macro and micro bridging by this method here. For example, for this case of single shear band here, we know that the shear band occurs along this right band here. Okay, we select 2 points. One is point B, point A. One is point B. Those are 2 Gaussian points here, and we observe those DEM or RVE response. We homogeneous from this DEM simulation here. So we first look at the point A here. The point A response typically will give us this loading and unloading. These are the stress strain relation here. Those are the volumetric behaviors here. Those are the stress paths, loading and unloading here. Okay, and those are the evolution of fabric tensor during the process here. So for point A is outside the shear band, we observe a typical loading and unloading process, and the volumetric contraction is relatively small. And also, the contact force network is represented by this. This is the contact force network, and those dashed square is the original RVE I showed here. So though the force network change is relatively mild, is small here. Okay, and so the fabric change is also relatively small. Now let's look at the Gaussian point B. Those RVE response, and we can extract this RVE response here. As you can tell here, the stress strain relation going to a hardening to a peak and then going down to a softening. And the contraction is also, the volumetric changes from this contraction and then to a excessive dilation for point B here. The stress path is going to this loading, peak, and unloading. And also the fabric evolution, both particle orientation based and particle contact based orientation, contact based fabric, they evolve extensively. Okay. But they evolve at the different peaks. And importantly, let's look at this so-called microstructure here. This again, this dashed square is a original RVE configuration here. And those are other RVE configuration and at like shear strain of 200% here. So the shear strain level is very large, and so this RVE or microstructure experience a severe distortion or shear distortions at the end of this localization. So this is one major feature that this multi-scale approach can allow us to really to establish a direct correlation between this macro scale observations with this underlying physics here. Okay, we see all these response here. So this is one feature that I want to show here. Okay, of course we can use the same framework to really simulate other phenomena like liquefaction. We apply this so-called global unjoined condition to a loose packing inserted at the Gaussian point, and we apply secular loading, and we can see that we can generate a typical response, and we observed in the lab test. This is a liquefaction behavior. We go through here to relatively very small stress levels here. And if we look at this Gaussian point and this RVE, and they are very small or to zero contact force established when this liquefaction occurs at this point here. So this is direct evidence where when liquefaction occurs on their vertical, there's no contact force established there. Effective contact established between particles. So this is another example. As I mentioned that we aim to solve engineering problem here. Here's one example I showed that we can use the same framework to solve a retaining wall problem here. And these are the soil behind this retaining wall shown here. And so the retaining wall can be either moved outside to the right and pushed inwards to the soil to the left, or it can rotate about the bottom, about this the top here. And so it can generate different passive and active state here. These are the different feeder mode. Okay, these are the passive mode. You can move, you can push this retaining wall to inside the soil. Okay, in the different mode to generate different feeder mode here. These are the active mode. Of course, we can further to correlate this results calculation with the classical retaining wall theory, those are baryon capacity theory, and to get a correlation here. Another example here, this is rigid footing here. We have foundation and we put a rigid footing onto the foundation here. Okay, and we want to really simulate the baryon capacity of such a footing problem here. These are the situation here. We just simulated half of this domain here, and we push down this footing, and this will generate such a localization parties like that. And this pattern is exactly that what Tasagi back in almost 100 years ago described as this by Tasagi's class scale theory. Okay, we can form typically our simulation captures that, but below this rigid footing, it form a rigid wedge here, and then it's form a radial shear zone, and then there will be a passive Rankin's passive zone here. Okay, we can further correlate the different measure, okay, with the prediction by this Rankin theory here. Okay. And we can extract further those classical strength parameters of the sand, and by doing DM simulation, pure DM simulation to extract those parameters and compared with our boundary value problem predictions here. And so this is regional wall problem. Another example I want to show here is this cavity expansion problem. For example, in the petroleum engineering, and they are quite concerned with this cavity expansion here. And we simulated a quad domain and this full domain. And this simulation, even though their load displacement curves are quite similar to each other. And when we simulate this quad domain and this full domain, we found that the development of shear bond along this along this circuit walls domains are quite different here. And indeed, we found that, for example, for the quartz domain, and even the symmetry is considered, but probably the results is not so real because the development of shear bond could be fakely induced by the boundary reflection here. Well, if you have a full domain, so the results will be quite different here. Okay. And so this is just another example here. And so, so far I introduced the continuum discrete coupling by FEM and DEM here. But FEM and DEM coupling cannot help us to solve a large deformation problem because there's some intrinsic constraint by that coupling. And indeed, we can easily replace the FEM by MPM here. We know that MPM is based on a combined Lagrangian and Euler descriptions to enable it to describe large deformation problem. In the same way, we can couple MPM and DEM together. We insert a DEM packing at each material point of this MPM. And according to the same loops, and we can solve a boundary value problem to establish a hierarchical coupling as well here. And indeed, another feature I didn't mention before is because each DEM packing for the RVE at each material point, they are independent with each other. And so if your computing resources allows you to really to take for example, a high performance cluster, you can really take advantage of this feature. You put each DEM simulation at each CPU cores, okay, or GPU cores, okay, and then do a parallel computing, and then this will greatly speed up your calculation. And I would confess that the computational cost of this multiscale coupling modeling is relatively expensive compared to the conventional continuum-based. So here's one example that we do this rigid footing again, but we prepared a foundation with different sand. Left is dense sand, and middle is medium dense sand, and right is loose sand here. Okay, we pushed it down and very deep here, for example, and with to large soil to experience a large deformation here. For the dense sand foundation case, we get this so-called general shear failure mode that we can find from this typical textbook of geotechnical engineering. And for the medium dense sand, we get this so-called local shear failure. As you can see, the failure is confined relatively small range. Okay. Well, for the loose sand case, and this we call a punching failure mode. This is the one example that we can capture the large deformation experienced by the sun under this rigid footing case here. Those are the further information we can extract, for example, the shear strain, the displacement, this Void ratio, and also this cumulative particle rotation at the different positions to really do a correlation analysis to analyze the failure mechanism of this the foundation and the different foundations and the same and rigid footing here. Another example I want to show is this is in the offshore engineering that, for example, we have a seabed pipeline interact with the seabed soil. Okay, and for example, this seabed pipeline, when we put it down and the gravity is going to really settle down a little bit here. Okay. And this excitement of this wave, sea wave here, is going to move laterally here. Okay, and so this simulation will capture, for example, the displacement as well as this shear strain and this combined gravity and the wave load, and for this to have this interaction between this pipeline with the seabed soil. Okay, and so the shear strain captures that the interlayered shear bond developed and to allow the soil to develop a very large deformation here. Another example showed here, again, it is in the offshore engineering, for example, the anchor pull out. We can have different anchors here, okay? And this top figure give us a plate anchor, horizontal plate anchor when we pull out vertically, okay? So it is embedded in the seabed soil. When we pull out, and so this anchor will experience a very large the soil surrounding the anchor will experience very large deformation. And so the soil below this anchor will also have maybe have a gap generated and during this process here. And when we look at this, for example, when we put the plate anchor in a vertical direction, when we pull it horizontally, this is another simulation that we can get here. Okay. And in front of this anchor, we generate this so-called passive mode failure. And behind this anchor, the sand will generate a so-called active failure mode here. And depending on the embedment depth, and so the failure mode will be quite different. For example, this will be a different burial depths here, a shallow, medium, and deep. When the anchor is embedded deep enough, so you can see the failure mode basically is confined locally. And so there will be a so-called transport of this sand and form in front of this plate to behind this plate here. So it kind of like a rotating failure mode here. So this is one thing that we captured by this coupled MPM with DEM. As I mentioned, that sand is porous medium, and the porous is always filled with partially or fully saturated by water here. Now let's see that how we can deal with the saturated granular sand. Again, that for granular sand here, and only saturated with water, according to the principle of effective stress by Tasaki. So the total stress can be decomposed by effective stress and forward pressure. Here, I just use a minus here to see that the different sand convention here. Okay. And so this is the principle of effective stress here. So our consideration is that we know that from a DEM simulation here. And when we homogenize this contact force, this will give us so-called stress here. And this stress is homogenized through this contact between particles. And this homogenization exactly consistent with what Tasaki has envisioned, that the effective stress, indeed, it is the homogeneous contact stress that we derive from the DEM simulation here. Okay. So this is a point that we want really to derive the effective stress from a saturated granular medium directed by the DEM simulation here. Okay. And we consider a coupled hydromechanical coupling problem with a coupling equation like this one. And we based on a UP formulation as proposed by Jingwei here. And we reconsider our hierarchical multiscale modeling here. Okay. Again, at each Gaussian point, we can consider both the displacement and pore pressure as two unknown variables to solve here. But we embed at each Gaussian point with the same DEM packing as RVE, and prescribed by this deformation increment and also pore pressure. Pore pressure will not be solved by this particle scale, but it will be regarded as a continuum variables here. Okay. And then this whole thing will be solved by using this RVE response to solve effective stress and then put further into this common equations to solve a global equation by this FEM here. And those quantities can further be derived by, for example, the permeability can be further correlated with this RVE response by this KC equation and other things here. Okay. And so we can benchmarked by this 1D consolidations with the Tasak's solution, and further benchmarked by this like 2D consolidation problems here. And before we apply to a boundary value problem, this boundary value problem is a saturated granular solid domain here. And the four boundaries is impermeable, and we compress we do a partial compression here. Okay, and those are the response here. And on the left, we compare to a pure DM simulation of the same domain. And we know that for DM simulation, if you don't consider water, normally an unjoined condition is imposed by constant volume. Here, the triangle is a pure DM with constant volume, and the red line is our boundary multiscale modeling here. You can see at some beginning point, and they are considered consistent. But once the localization is triggered, so the boundary value multiscale modeling will deviate from this pure DM simulation. So that's the indication that we're on the right-hand side. You can see here. Those errors indicate when the localization occurs, and because it will generate a inhomogeneous Ward ratio field here in the whole domain. And so the water will flow from this high pressure to the lower pressure here. So those errors indicate the Darcy flux, the Darcy flux and during and after, right after this formation localization here. But those only occurs transiently. And when the localization is fully developed, and so there will be no Darcy flow occurs. So this is the example that we show that how we can couple the water with a multi-scale framework here. And so as I mentioned, the whole idea of the framework is open in a way that we can incorporate any continuum approach, the development continuum approach, and also we can incorporate any latest approach development in the meso and micro scales, okay, and to enhance the functionality of this approach. For example, any further development in the DM levels, we can incorporate the shapes, and by using ellipsoid shape, super ellipsoid shape, and polyellipsoid, okay, and we can further want to map a realistic particle sun shapes. We can use Fourier shape descriptors, or we can further map this X-ray CT scanners and map that directly to a DM simulation, and then further incorporate this DM to a multi-scale model here. Those are all doable here for this multi-scale model here. And also, if we further consider that where the particle crossing is important, we can, for example, we can incorporate the simulation by paradynamics. This is things that we use paradynamics to simulate a single particle crossing here. And this is quite different than the clumped particle DM approach here. And we can further, for example, to reconstruct the crushed particle fragment, the charged particle, and then further put it in a packing. For example, here we propose to combine this paradynamic simulation with this non-smooth contact dynamics simulations to simulate the continuum grain crushing problem here. Okay. For example, this crushing, this paradynamics will return this crushed charged particle information to this non-smooth contact dynamics, and then the contact dynamics will return key information for the paradynamics to judge whether or not a particle is crushed here. Okay, and we can use some open source code related to this coupling here. This is an example of this continuum grain crushing here. For example, when we do 1D compression and for a crushable granular media. And so this will be the process that we generated by this coupled non-smooth content dynamics with the paradynamics here. Okay, and here's a initial packing here, and when the crushed midway when we increase the pressure and further increase pressure to a very large compression pressure here. These are the number of particles increased from around 600 at the beginning to about 30,000 here. Okay, of course, if you continue to crush it, and so this approach won't limit the number of particles here, as long as your computing resources allows you to do so here. So those are the examples that you can further incorporate those interesting physics into your the multiscale approach. For example, we can further incorporate this thermo-mechanical loading and to really do exactly like a thermal loading coupled with mechanical loadings, and to see how a granular problems respond to this coupling process. Okay, and it's quite easy to extend it to other material like granular rocks here. And we can incorporate the bounded particles in the DEM here, and to simulate a granular rock. Like here at the left, it is showing as a simulation of compression band to shear band transition in a saturated high porosity sandstone. Okay, and here the arrow showed this is the Darcy flux of the water during this compaction. So the compression band formed in the middle of the granular rocks here. And then further, when the loading further going on here, there'll be a shear band and formed during the process. On the right-hand side is a simulation of a compression front. Okay. And by a comparison between this X-ray CT scanner observed in the lab test here and with our simulation here. So this is the first thing that you can easily incorporate these bounded particles in this DEM and further to simulate other material here. Okay. And I still have four slides. It's quite soon. I'm quickly going to another that we do this multi-physics modeling. I use this debris flow as one example here, because debris flow is pretty important locally in Hong Kong. Okay, and so we simulated debris flow by combining two masks. One again is DEM, with the DEM to simulate a. Sorry, here this is wrong. DEM simulates this cost debris, this granular system here, with the CFD to simulate a we call slurry. The slurry consists of water and foam. So the whole debris will be split into two systems. One will be a slurry, and one is a granular system by DEM, and a slurry by CFD here. Here's I put it wrong here. Okay, and then here's one simulation that we use this coupled CFD and DEM to simulate a mixture of this one to get it down to a natural terrain, and compared with a pure slurry, like a pure CFD simulations and also pure DEM simulation here. Okay. But our purpose is really to do the mitigation. The mitigation is really, now we emphasize to really use this flexible barrier and to mitigate the debris impact here. And so the whole framework, we can use DEM to simulate the flexible barrier by developing a so-called lumped discrete particle with remote induction. And also we can simulate it now, recently we can simulate this ring barrier here. Okay, so here's the simulation that the interaction between these particles and the fluid, the slurry, and the flexible barrier here. Okay. The three interaction we can capture by this way and to quantify the impact of this debris flow and on a flexible barrier and for design purpose. Okay, these are the further demonstration of this multi-physics simulation here. So I don't have a conclusion. So this is what I wish to introduce, what we have been doing for the multi-scale and the multi-physics modeling. But before I end, I wish to acknowledge the financial support of all this Research Grant Council of Hong Kong, the Natural Science Foundation of China, and also other agencies here. And wish particularly to thank all my past and current students, PhD students, and my postdocs. Okay, with that, thank you.
Thank you very much, Jidong. That was an excellent presentation, very, very interesting, with some very, very advanced simulations. So that was great. I should say that this webinar is being recorded, and a link to the recording will be sent out after the webinar once once everything has been processed. So that should be available very soon. So we will open up for questions, and there's one hand raised, Deng Ming Wang. It's been raised throughout the talk, so I don't know if it's a mistake but I will allow you. Okay, maybe it was a mistake. Okay, let's take some written questions then. Now, Jidong.
Yeah.
And I see that as this is a question as well, but this was a question of my own as well. The size of the RVE.
Yeah.
So the necessary size of the RVE, how many particles do you really need at each Gauss point?
That is a good question, because RVE is important. For one hand, we want to have a very big RVE to include enough number of particles to faithfully reproduce the material response like we observe in the lab, right? Okay. On the other hand, we don't want we don't want a lot of particles, because that will be increase the computational cost a lot here. So in practice, what we have done in our 2D simulations, for typical 2D simulation, and we do a kind of like a consistency study, and by generating different criterion. And we found that for a 2D study, we about like 400 to 600, those kind of range will give us reasonable response of material response, as well as the consistency and computational efficiency.
When you say 2D, is that the macro? And that was another question, really, maybe you can answer that as well. You showed a lot of 2D problems, slope stability, foundations, and so on.
Yeah.
Is it 2D at the particle level as well, or is it 3D?
Yeah, indeed, for the continuum level or for the particle level, they are both 2D in a way that we limit the out of plane direction, their degree of freedom. We just retrain their degree of freedom.
Sure.
Yeah.
And how then do the actual calculations? You had a slide that showed sort of this top down, bottom up, but I didn't quite get that. Is it a kind of an implicit approach at the end of the day, where you get where you somehow derive? I guess numerically it would have to be a tangent modulus, a tangent operator, or is it? How does that work?
Yeah, for the FEM coupled with DEM, because FEM we need this so-called convergence thing. We need iterative schemes really to solve it here, to solve this problem. And there are different ways to really to get the solution converged. And one would be so-called people do this so-called perturbation. Perturbation means that how you can get this tangential operator. Basically, you do a perturbation of different string levels really to get a different response to get this tangent. But that one is not always reliable in a way that sometimes you cannot get a solution. The solution is not converged. Okay. And so what we've done is we do a so-called approximation, and in the first place, we don't get this tangent operator, and instead we use this second stiffness as approximation. of this. So we get a so-called the elastic stiffness of deformed RVE, and we derived that as a approximation to this tangent operator, and then but we do iterations try to really do before it reached a convergence, and that's a way that we found that the solutions, the convergence is pretty good.
Yeah. So this is an implicit scheme.
Yeah. For the finite element method, finite FEM coupled with DN, we use the implicit one.
Okay. Yeah,
and but for the MPM and the DM, and indeed, our first stage of solution, we use the explicit because both DEM and the MPM, and they are based on the explicit. But later on, now currently I have a student working on this capital problem, the saturated soil simulations, and we developed this semi-explicit approach.
Okay, great. Let's see what we have. Yeah, the undrained problems you showed there, Jidong, where you had a difference between the full DEM and then the multiscale approach because of the flow, you say.
Yeah.
That would depend on which you load the sample, right? Or no?
Which one?
Yeah, I think it's a little further. You had the full an undrained sort of biaxial test, I guess it is.
Yeah, here.
And then you have the full DEM versus multiscale.
Yeah, here. Indeed, for the full DEM simulation, basically we apply this spectral shear. But for DEM simulation, we can also restrain the volume, with constant volume spectral shear here. Okay, and so it's essentially the loading is quite similar to this this spectral shear, the boundary value problem here. But for this boundary value problem, we have this hydromechanical coupling. We consider power pressure. And so once the localization occurs in this boundary value problem here, and then you see here the simulation by pure DM and this one, basically they divert with each other, and that is because first of all, this onset of shear band. The other is developed from this excess power pressure, not excess. The flow inside sample, the flow here, and that will trigger this difference here.
Yeah, but won't that depend on the rate of loading? When you have a flow that progresses at a certain rate, and then wouldn't that be somehow affected?
Well, in our simulation for this one, we still do it. We can do it in a quasi-static. Of course, when we consider permeability, right? Okay, there's a time scale here. Of course, there will be naturally a loading rate, but somehow we can still really do a quasi-static loading for this one. And of course, in reality, you cannot do that, right? Okay. And numerically, you can hold on to certain states. So the loading is still a quasi-static loading.
Okay. All right. Okay. Just back to the RVE, there's an interesting question. What are the boundary conditions applied to the RVE? So is it displacement, or let's say strain boundary conditions, or is it stress, or is it something in between? Because all three options are in principle.
We use periodical boundary conditions, and basically is a displacement boundary here. Okay, and indeed the boundary conditions, and we apply for this deformation gradient is a strain and displacement one, but it's periodical. Of course, there are different options here, but the main consideration is here when we do this multi-scale modeling, and we want to derive the DM as a material response. And so we homogenize that, and by assuming that this DM simulation will give us a homogeneous deformation rather than generate shear band. So that we want to really apply pure boundary to prevent the shear banding inside the DEM simulation, so that we can get a homogeneous deformation inside the RVE.
Yeah. And a comment, again, returning to something we talked about a minute ago, the use of 2D DEM. You could use 3D particles even for 2D simulations, of course, right? So
yeah, of course.
But of course, 2D is cheaper, so I guess that's the motivation for.
Indeed, at the beginning, from the very beginning, and I've talked to my students, we develop everything from 3 dimensions because we don't normally do the whole thing again. So our FEM and the DEM basically are full 3D at the beginning. But because at the beginning we don't have in my university, I don't have access to this high performance computing facility. And we can only do this server workstation stuff, and so I have really to limit this the scale. So I do a lot of problem in the 2D.
And just on, could you say a few words on the computational architecture and so on? I mean, these simulations are impressive, and they require a lot of number crunching, right? So I guess parallelization is absolutely essential. So the Gauss point RVE type calculations can be done in parallel.
Yeah,
I'm assuming, and you would want to do that. Otherwise, it wouldn't be really practically feasible to solve very large problems.
Now the reason that now we can go on 3D because we have implemented this parallel computing now, and we can access now this our cluster in the university, and we also access our national supercomputer centers, their computers here. We can use a lot of CPU cores, and we assign each CPU cores with one RVE, one DEM simulations, and then let it go. And so really depend the scale of the problem really depends on the computing resources you have. So
yeah. Let me just see if there are some. So there are some raised hands. Let's try to take one of those. Carlos Vaca, I'll put you on. And you should be unmuted very soon. Well, I don't know why that is not happening. I'm trying to unmute you. Okay, we'll go to the next one. I think you might have.
Hello.
You guys. Yeah, hello.
Yeah, this is Yiming from Georgia Tech in USA. Thank you, Dr. Zhao, for the impressive presentation and beautiful simulations. I have a question. Could you please comment on the computational cost and the implementation difficulty for the FEM DEM and the MPM DEM approach? Thanks.
You mean computing the cost? Indeed, it's quite I would say that one of the motivations of this hierarchical modeling is we don't want to have a full domain DEM simulation. For example, if you want to simulate a slope and use totally the realistic particle size for a slope, it's unaffordable for all of us. And that's why one really extract this, unbound a RVE in the Gauss point of a continuum method like FEM and MPM, and to get a material point to get this multiscale modeling. But still, I would say that the computational cost is much higher than the traditional continuum approach that purely based on FEM or MPM, because the major computing cost is from this the RVE calculation here. That's why we developed this parallel computing, the MPM and other kind of parallel computing techniques to distribute these RVE calculations to different a class, different nodes class, and try to really to speed up the whole thing. And so this is what we have done. So, but I would say I am not very concerned of this computing cost now, because as long as you have this, you have access to this high performance computing facility, and that won't be an issue.
Gotcha. So how about the implementation difficulty, which means how difficult will you implement your algorithm? I mean, build your model like this.
Well, you know, we would say that we stand on the shoulder of giants. We didn't really develop everything from scratch. That's always probably one of the strategies I always advise my students. And we develop everything from the open source code. For example, originally we have this FEM, and we have we get this open source FEM code we call eScript, and we that open source code. And for the DEM part, and we use this YADI, and this open source here. And so we got open source, and so our student will develop some interface like using Pythons and other code to really do this coupling. So once you get all the source, all the things, and you can really optimize the whole process, and then to further implement whatever the parallel computing strategies. So I would say that we take advantage of this open source, and also our part of our code, like this FEM DEM coupling, we have made it open source as well. You can really find this source code examples and this example or data file and other things. All the source code in the YADI website. You can download it. You can even contact me and my student for any technical questions about that.
That's great. Thanks for that, Jidong. And Carlos, I don't know if you want to unmute yourself and ask a question. So then there's Javier.
Hello, Professor. Thank you very much. It was a very nice presentation and very stimulating. I have just one question. Did you find dependence of the internal of the strain localization bandwidth with the internal pore pressure?
Oh, with what? With the pore pressure, right?
With the pore pressure. Yes.
Well, I would say that you mentioned a good point in a way that I didn't mention during the presentation here. Our multiscale modeling still based on so-called first order coupling. First order means that for example, for the FEM, we have not considered a higher order terms in the whole thing. So much the bandwidth and the mesh size could still have some dependence, but this is something that we didn't really focus on. We just want to capture this phenomenon. So that's the answer.
Okay, like a strain gradient plasticity, for example.
Yeah. Of course, strain plasticity and other non-local method, you can really use that kind of strategy formulation, try to regularize the shape and width.
All right. Thank you very much.
Thank you.
Sorry, I should unmute myself as well. Thank you. I think we should probably end it here. these questions can continue, and I would encourage you to get in touch with Jidong for further discussions. But it was a really interesting presentation, and thanks a lot for participating in the discussion as well. So as I said, the webinar is being recorded, including the discussion, and a link will be sent out to the participants shortly. Just to remind you that we do have another webinar coming up in 2 weeks. An invitation will be sent out for that as well by Professor Itai Aina from the University of Sydney, who will talk on subjects that I believe will be somewhat related to what we have heard today. Not necessarily multiscale modeling, but definitely granular materials are going to be, I think, safe to say, at the center of that presentation. It should be really interesting. So be sure you catch that, and thanks for your participation here today, and hope to see you next time.
Thank you. Thank you all. Thank you, Christine. Right.
Yeah. And Jidong, just hold on so we can have a little chat
yeah, sure.
afterwards. Okay, thanks.